Hello students, good time to all. I am Chandan Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss experimental verification of Planck's law of blackbody radiation. Let's begin. In the previous video lecture, we have already discussed the theoretical result of Planck's law of blackbody radiation. Here, we show how that Planck's law of blackbody radiation can be experimentally proved. There are so many scientists who try to prove Planck's law of blackbody radiation experimentally, but we have to discuss one such experimental arrangement that performed by two scientists. One is Leumer and another one named as Frenxium. Leumer and Frenxium took an electrically heated chamber with small aperture as a blackbody which provides radiations. This specially radiating chamber fulfills the condition of blackbody radiations. This is a chamber which electrically heated, that one is a blackbody, and that blackbody radiates radiations, and that radiating chamber fulfills all the conditions of blackbody radiations. A narrow slit S1 culminates the radiations into a narrow beam. These radiations from that of blackbody radiators is culminated by the narrow slit, that is a narrow slit S1, narrow slit S1, through which the radiations are culminated. Radiations are passed through that of narrow slit S1. The beam is allowed to fall on a stainless steel, that the stainless steel of concave mirror M1, which reflects the blackbody radiations. Here we use a concave mirror. This is a concave mirror M1. The culminates beams from that of blackbody radiators incident through that of slit S1 at that concave mirror M1, which one is stainless steel. The distance between the slit S1 and concave mirror M1 is equal to the focal length of the mirror, so that the parallel beam of radiations emerge. That is the condition. The S1 and M1, what be the distance in between this? That the distance is equal to the focal length of that of concave mirror M1. Why? As that radiations are incident on that of concave mirror M1, after that incident these are reflected parallelly. To reflect parallelly, the condition is the distance in between the concave mirror M1 and S1 should be the focal length of that of concave mirror M1. The parallel beam of radiation is then allowed to fall on a rock salt or fluorosphere prism P. A prism P which is made up of either rock salt or fluorosphere material. Why we use fluorosphere? Because through that type of fluorosphere infrared radiations are easily passed. Here it is a prism P, that the prism is made up of either rock salt or fluorosphere. Why? The fluorosphere substance is transparent to the infrared radiation. Therefore, we use such type of material in that of prism. That is not normal prism. That prism is made up by these materials, and that prism is placed on the turntable of a spectrometer. That prism we set up to the table, turntable of a particular spectrometer. The emergent beam falls on that of concave mirror M2. Here the incident radiations on that of mirror M1, they are parallelly immersed. Through that of prism, the phenomena like refraction, then dispersion, the emergent beam falls on a concave mirror M2. Here we take another concave mirror, named as M2. These rays are parallelly incident on that of concave mirror M2. The different wavelengths of radiations are brought to focus at different points. The beam is focused by the reflecting mirror M2 on a thermopile or a bolometer placed behind another slit S2. Here we take a slit that is S2. After that emergent beam reflected on that of concave mirror M2, they are through that of slit S2. On that of slit S2, we use a bolometer or thermopile. B. Why we use a bolometer or thermopile? That bolometer is sensitive to heat. That blackbody radiations are now incident through that of M1 then through P incident on that of M2, then through that of slit S2 to that of bolometer circuit. The beam is focused by the reflecting mirror M2 on a thermopile or bolometer that placed behind another slit S2. The bolometer B, instead of bolometer we can also use a thermopile, which is sensitive equipment to measure heat radiation. That bolometer is sensitive to heat. In which way that is sensitive? That a heat radiation is proportional to the deflection in the galvanometer. What is the use of a galvanometer? That a galvanometer is connected to that of sensitive bolometer. The bolometer is connected to a sensitive galvanometer Z. That bolometer is connected to a sensitive galvanometer Z. Therefore, the intensity of radiation is proportional to the deflection in the galvanometer. The amount of heat radiation if increased, then the deflection we can measure by using that of galvanometer. In this way, the intensity is measured through that of equipment bolometer. This is the experimental setup. By using that experiment, what are the result we obtained? The result as that experimental setup to show either Planck's law of blackbody radiation is exactly matched to that of experimental data or not. To show that, a graph is plotted in between wavelength, this is the wavelength, lambda along x direction, and the emissive power, or we call it as energy density, E lambda, emissive power, E lambda along y direction, at a particular temperature we plot a graph. At a particular temperature we obtain a graph like this at a particular temperature. That graph is exactly same to that of theoretical expression proposed by Max Planck regarding blackbody radiation spectrum. That is exactly matched. This is the experimental curve, is same to theory. That experimental curve is same to that of theory. As we taken that the bolometer is sensitive to heat and that bolometer is connected to a galvanometer Z. So, the deflection is measured through across that of galvanometer and the intensity of radiation is proportional to that of deflection of a galvanometer. In this way, we measure a graphical view regarding wavelength and emissive power, and we obtain that graph which is same to that of a theory proposed by Max Planck regarding blackbody radiation spectrum. And that particular graph how deviate to that of Rayleigh-Jeans law. According to Rayleigh-Jeans, if you plot a graph between wavelength and emissive power, that graph is like this. This is the graph of Rayleigh-Jeans. Jeans law graph. as lower the wavelength, it is at higher the wavelength, it is same to that of experimental curve, but further it is deviate to that of experimental curve, and that deviation we call it as ultraviolet catastrophe. That spectrum we see in that of ultraviolet region. We have discussed it. Next, in that of Wien's distribution law or Wien's displacement law, that is deviated from that of experimental curve like this. This one we called Wien's displacement law. Graph. That one the result of the experimental arrangement to verify Planck's law of black body radiation. So, here with the help of this video lecture we understand experimental verification of Planck's law of black body radiation. This is the experimental arrangement proposed by two scientists Lumor and Frenchium. This is the experimental setup and the result obtained from that of experiment, which is exactly same to the theoretical data proposed by Max Planck regarding black body radiation spectrum. In that of graph we show how it is exactly matched to that of experimental data, and then how it is deviated from Rayleigh-Jeans law and Wien's displacement law. So, with this useful and informative notes, let me wind up the session. Thank you.